Let's begin this review with the following problem, considering the data set 19, 9, 5, 1, 12, 6, and 4 for x, and the corresponding y values 0, 4, 12, 7, 9, 7, 3. The first part is to find the 5 statistics summary. The first part of the 5 statistics summary, of course, is just simply getting the mean and the standard deviation. So the average of x and the average of y, and also the standard deviation of x and the standard deviation of y. Just using Excel, the average of the x values works out to be 8, while the average of the y values works out to be 6. And the standard deviation of the x values works out to be 6, while the standard deviation of the y values works out to be 4. That's using Excel. There are also commands on the TI calculator, which if you input the list, you will get the x and y values. Next thing we need to get is x in standard units and also y in standard units. And to do that, we have each x value, so 19 minus the average of the x's, which is 8, divided by the standard deviation of the x's, which is 6. So 19 minus 8 is 11, divided by 6 works out to be 1 5/6. And then we do that for all 7 of the x values. And likewise, for the y values, we take the y value of 0 minus the average of the y values, which is 6, divided by the standard deviation of the y values, which is 4. So negative 1.5. And then filling down, we get the y values converted to standard units. The next step is to get the products of all the x and y values. So x in standard units times y in standard units. And then we take all 7 of those products. And so finally, the correlation coefficient, r, will be equal to the average of these numbers, except I divide the sum not by 7, but by 6, by n minus 1. So finally, the r value works out to be, in this case, negative about 0.493. So that is the computation of the 5 statistics summary. There are shortcuts for doing this both in Excel and on your TI calculator, and you're welcome to use those shortcuts if you want. The next part of the question was to find the equation of the regression line. So let me write down the important information here, that x bar was equal to 8, while the standard deviation of x was 6. Y bar worked out to be 6, while the standard deviation of y was 4. And the correlation coefficient we worked out to be negative, I believe, 0.491 approximately. 493, I'm sorry. Okay, so the equation of the regression line, if you know the y value and you're predicting, if you know the x value and predicting the y value, the regression line is y minus y bar is equal to r times s sub y over s sub x times x minus x bar. So y minus 6 equals negative 0.493 times s sub y, which is 4, divided by s sub x, which is 6, times x minus x bar, which is 8. So solving for y, we get y is equal to, well, let's work out the product here. So the slope of the regression line would be equal to r times s sub y, which was 4, divided by s sub x, which was 6. So I get a slope of negative 0.3287. times x minus 8 plus 6. For part 3 of the problem, if I know the value of x, which is 10, then the predicted value I get by just simply plugging in. So this was part 1, part 2 is here. So for part 3, the predicted y value would be equal to negative 0.3287 times 10 minus 8 plus 6. And so the predicted y value would be equal to this slope that we just found times 2 plus 6. So for 5.343. To do problem 4, your first temptation might be to let y equal 10 in this equation and solve for x. Unfortunately, for problem number 4, we have to find the other regression line. This regression line that we have currently, this regression line applies if x is known and y is what's predicted. Here, y is known, and so I need to predict x. So to do problem number 4, I basically need to find the new regression line. So let me start taking off information here that I don't need. This was for problem number 2. For problem number 4, the regression line that I need is obtained by interchanging the roles of x and y. So basically, everywhere I see an x, I replace by y and vice versa. So s sub x over s sub y times y minus y bar. So this would be the prediction line for if y is known and x is unknown. Okay, so now that I have that, let me get rid of number 2 here, just to clear off some space. And also let me get rid of the information up here just so I can get some extra space on the screen. Okay, so in our question we have x minus x bar, which was 6, equals negative 0.3, negative 0.493, the value of r, times this time s sub x over s sub y, times y, the given value of y is 10, minus y bar, and the average of y was 6. And so for problem number 4, the predicted x value would be equal to this r value times s sub y, x over s sub y times 10 minus the average of y, which was 6, plus 8. And I see that on the screen here I made a mistake, that this 6 was incorrect, and it should have been an 8, the average of x. Okay, so x minus x bar is equal to r times s sub x over s sub y, y minus y bar. The average of x is 8, the average of y is 6. So plugging into the equation here, we get the predicted x value to be 5.041. And so that's the predicted value of x given y. And again, I had to use this new regression line because of the way the question was phrased. For problem number 5, we have to test for find a 95% confidence interval for the slope of the regression line. To do this, we will use the error that can be found for the estimate of the regression line. So SC equals S sub y times square root of 1 minus r squared, square root of n over square root of n minus 2. So in our problem, we have that S sub b, the error estimate on any predicted value, would be S sub y, which was 4, times square root of 1 minus negative 0.493 squared, times the square root of 6 over 5. So doing the arithmetic over here, let's see, let me do it over here. S sub e is equal to 4 times the square root of 1 minus r squared times the square root of 6 over 5. So I get SC to be 3.8121. And then knowing this information, we can now get the standard error for the slope. And the formula for the standard error for the slope is on the screen. There's actually 3 ways of doing it. We have S sub b over S sub x over square root of n minus 1 using the information we just got. Or we could have directly done S sub y over S sub x times square root of 1 minus r squared over n minus 2. Or we could have had the slope over r times square root of 1 minus r squared over n minus 2. All 3 of these correctly give the standard error for the slope. In our case, since we've already done S sub b, let me use the first formula for no other reason, but we've already done it. So the standard error for the slope is equal to the S sub b that we just got, 3.8121, divided by the standard deviation of x times the square root of n minus 1. And in this case, n was 7, so we have square root of 6. So the standard error for the slope is equal to, and let me change this so that I can actually see that. Now, Caply didn't work out, oh well. Equals the standard error for the slope, 3.812, should have written down, divided by 6 times the square root of 6. So about 0.2594. So the standard error for the slope, and this number here, which was not a 4, but it was a 2, and that worked out to be 0.2594. And I'm not going to do it here, but you should get the exact same answer using either of these other 2 formulas. Okay, now that we have the standard error for the slope, let's now figure out the 95% confidence interval for the slope. So the 95% confidence interval well, the slope that we got before was negative 3.287. That was our estimated slope, plus or minus basically a margin of error. Now the standard error we just got is 0.2594. And this number is going to come off the t distribution. So I have the t distribution, and I need 95% of the area to lie in the middle. And in this case, I have a t distribution with 5 degrees of freedom, because 5 is equal to 7 minus 2. The number of degrees of freedom is the number of points. In this case, I had 7 points, 7 x and y coordinates, so 7 minus 2. Okay, so now I need the t value to go with this, and so that is equal to, let's see, in this case, t dot inv dot 2t is probably the easiest thing to do. 0.05 with 5 degrees of freedom, so for 2.5706. And so that's the number that appears here, 2.5706. So negative 0.3287 plus or minus. Okay, so the margin of error will be equal to this number times the standard error for 0.6668. Now notice that is a very, very wide confidence interval because we had a pretty small value of n was only equal to 7. Lastly, we need to test for a negative slope of the regression line. So in this case, the null hypothesis would be that the slope of the regression line is equal to 0. And the alternative would be that indeed we have a negative slope. And so the t statistic would be equal to the observed slope minus the expected slope divided by the standard error for the slope and so this gives us a new t-value of the slope, which we found to be here, divided by the standard error for the slope for negative 1.267. And so doing the work over here on the side, we once again will have a t distribution with 5 degrees of freedom. And the p-value will be the area to the left of negative 1.267. And so the p-value would be equal to t dot dist of the number we just got. 5 degrees of freedom, it's cumulative, and so we get 0.1304. That number is bigger than our default value of alpha, and so our decision will be to retain the null hypothesis. So in words, we retain the null hypothesis. There is not enough evidence to suggest the population slope is negative, is not 0. And that's not, again, too surprising because we only had a sample of size 7. Perhaps with a larger sample we would have a different conclusion.